If you've ever found yourself wondering exactly why the solid ground suddenly decides to shake violently, well, you're in the right place. Let's get right into it. We'll be breaking this down using a simple rule of three to categorize how the Earth's crust interacts. First, we'll look at the Earth's moving puzzle as a whole. Then, we'll cover the three boundary types: pulling apart, crashing together, and finally, slipping past one another. All right, Section 1, the Earth's moving puzzle, the engine beneath our feet. So as we know from plate tectonic theory, the Earth's crust isn't just one big, unbroken shell. It's actually a dynamic mix of solid continental and oceanic plates. And what's driving them? Deep thermal convective currents miles below us. Think of it like a giant, slow-moving pot of boiling soup, pushing the pieces around. To really wrap our heads around the immense planetary scale of this puzzle, let's look at the numbers. The Earth's crust is fractured into 6 major plates. We've got the Eurasian, the American, the African, the Indian, the Pacific, and the Antarctic plates, alongside 20 minor plates. And here's the kicker: they're constantly in motion relative to one another. That means every major tectonic event basically takes place right at the boundaries where these giant puzzle pieces meet. Moving on to Section 2, pulling apart, constructive boundaries. This is the first of our 3 major interactions. Picture those deep thermal convective currents pushing hot matter straight up from the asthenosphere right into an ocean ridge rift. This upwelling actually forces the plates to move in opposite directions. They're literally diverging or pulling away from the mid-oceanic ridges. Now, because this pulling apart is a relatively slow process, and the upwelling of basaltic lava through fissure flows happens gradually, the earthquakes here are generally moderate. They also have what we call a shallow focus. This means they originate just 25 to 35 kilometers deep, which, geologically speaking, is pretty close to the surface. To ground all this theory in some real-world geography, you'll actually find these constructive boundaries along massive underwater mountain ranges. We're talking about places like the Mid-Atlantic Ridge, the Mid-Indian Oceanic Ridge, and the East Pacific Rise. It is essentially brand new Earth being born right at the bottom of the ocean. How cool is that? All right, Section 3, crashing together, destructive boundaries. And fair warning, this is where things get far more violent. So if constructive boundaries are a gentle, slow pull apart, destructive boundaries are a terrifying head-on collision. Here, 2 convergent plates slam into each other. The immense pressure forces the heavier plate to subduct, which basically means diving underneath the lighter plate along a region known as the Benioff zone. This intense process of subduction leads to central explosive volcanic eruptions, deep faulting, and incredibly violent earthquakes. The contrast between these two is just stark. Remember those shallow, moderate quakes from pulling apart that maxed out around 60 kilometers deep? Well, destructive boundaries crashing together triggered disastrous earthquakes with deep focuses reaching down to a staggering 700 kilometers. That is a massive difference in depth and destructive power. Because of this aggressive convergence, certain parts of the globe experience the absolute maximum occurrence of severe earthquakes. The 2 most prominent global impact zones: the Ring of Fire, which is the circum-Pacific belt ringing the Pacific Ocean, and the mid-continental belts along the Alpine Himalayan chains. But here's the really interesting takeaway. While we call these boundaries destructive, they literally build some of the most dramatic features of our Earth. For instance, the subduction of the Pacific Plate beneath the American Plate is the exact massive force responsible for pushing up the majestic western coastal margins of North and South America. It's the reason we have monumental mountain ranges like the Rockies and the Andes. However, we can never forget the very real, chilling human reality of these geological forces. A prime example documented in our source material is the devastating January 26, 2001 Bhuj earthquake in Gujarat, India. This severe disaster was the direct result of reactivated subsurface faults triggered by the subduction of the Indian plate deep below the Asiatic plate. It is a stark, sobering reminder of the sheer power right beneath our feet. Now for Section 4, slipping past conservative boundaries. This is the final interaction in our rule of 3. At a conservative plate boundary, crust isn't being created like it is at a constructive boundary, and it isn't being destroyed through subduction either. Instead, 2 massive plates furiously grind and slip past each other without a direct head-on collision. But, don't let the lack of a collision fool you. This sideways motion creates extreme friction and intense states of disequilibrium, forming what geologists call transform faults. To put this into a real-world context, our source actually notes that the, quote, creation of transform faults along the conservative plate boundaries explains the occurrence of severe earthquakes of California, unquote. That exact mechanism makes it one of the most famous, active, and closely monitored earthquake zones in the entire world. Let's break down exactly how this operates step by step for California. Step 1, immense tectonic forces push one part of California to move northeastward. Step 2, simultaneously, the other part of the landmass is dragged southwestward along the fault plane. And step 3, this intense opposing movement creates a transform fault. The Earth literally snags, builds up incredible friction, and then violently snaps back. And that snap, that's what triggers massive surface-rupturing earthquakes. So, we've covered the pulling, the crashing, and the grinding of the tectonic plates that make up our world. I want to leave you with a final thought today. Knowing that we live on a constantly shifting puzzle, powered by immense, unseen thermal forces boiling and grinding away miles beneath our feet, how does that change your perspective of the solid Earth you stand on? It certainly makes you appreciate the dynamic, living nature of our planet just a little bit more, doesn't it? Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.